So like you were saying, start today by opening this day 4 AM digital data visualizations file. Okay, so open this file up. And I want to do this recently when we've been um, you know, when we've been doing the lectures so far, we'll go over some of the stuff on the HTML file, and then we'll switch over to R and do it in an R script. I think we should just do it right in this .qmd file, because then you'll have it, can save it on your computer, and it's not, it's not somewhere where we don't know what it is, and how it connects to the material will be obvious. And in the end, you can render this file again, and you have your own HTML notes with all the extra things that you've added to it. Okay, so today we're going to start. We're going to talk about data visualizations, which is one of my favorite things. Probably the thing that drew me to statistics was visualizing data. It's something I enjoy a lot, and something I probably spend way too much time on when I'm creating data visualizations, fine-tuning them, and things like that. But I really just think they're so powerful. And you hear a picture, I can't even think of how's that saying go? Picture worth 1,000 words. Thank you. I knew there's a picture, there's 1,000 words. I wish there. I'll start with a story here. So in 1870, in the London, in the Soho neighborhood, there was a cholera outbreak, and the public health officials at the time, they thought it was due to rotting organic matter. And there was a physician by the name of John Snow. He didn't agree with this, that it came from rotting organic matter. So he went door to door, and he asked people, hey, has anyone in this house had cholera? Have they not had cholera? Found out where all the cholera cases were. And then he plotted them on a map of London. And then there was a water line that he plotted along with the cases. And you can see all the cases were very close to this one water source, which that's not going to be the case when it's from, organic material. It's actually coming from the water. And this is something we know about cholera at this point, that comes from contaminated water a lot. And so the city health officials, they saw this map and they were like, okay, yeah, shut down the water source, and the cholera outbreak ended in a couple days. So data visualizations can create a very interesting story. And I think it's because of how good humans are at picking up patterns visually. I mean, we have been around for hundreds of thousands of years using our visual sense to pick up patterns, whether it's patterns in the way the land is, patterns in the way something is moving in the trees when we're hunting, something like that. But we have a very attuned sense of trying to being able to pick up patterns from sight. And so we're gonna take advantage of that, and we're gonna use plots to help us visualize data. And I think a good plot can really tell such an interesting story, if it's done the right way. Here, so it's something that we're going to use. A lot. The package we're going to be using here today is something called ggplot2. This is a very big package. I'm just going to Google search ggplot2 book. There is a whole book about ggplot2. I do not know all the things ggplot2 can do. Going back to what I said earlier, this is not about memorization. It's about knowing the concepts and having some understanding of what you can do, so then you can look it up. ggplot2 can do so much. Basically I look things up almost every time. So there's so many little options. So here it's just about having some understanding of what is possible, and then you can use the examples here, or looking things up on Google or AI to help you out. Okay, so ggplot2 is part of the tidyverse. Okay, so when you have library tidyverse, that's going to load up ggplot2. It's one of the most downloaded packages in R, one of the most used packages. There's a few different aspects that we're gonna work with here today. Clearly, the data is a key component of any plot we're going to make. The next component that we'll talk about is the aesthetics, which is this AES command. And what we use the AES command for is to tell ggplot2 things like, what's the X variable? What's the Y variable? Is there a grouping variable? How do we want the colors to go? The shape, the size, those kind of things. The next critical aspect is the genomes. So this is the type of geometric object that is going to be represented on our plot. These could be points, could be lines, this could be box plots, violin plots. There's all different kind of genomes that we can use. So those are the three, these three aspects have to be in every plot. You have to have data, you have to have the aesthetics part, tell it what the X and the Y is, or just the X, whatever it is. And then you have to have a genome. What kind of object am I showing? Those are kind of the hands down, we have to have those. The next one in terms of importance to me is the facets option. So the facets option is when you're making multiple plots side by side. So you're telling ggplot, hey, how do I want to make these side by side? How is that going to work? And then from there, so those things are all kind of basic, kind of simple. Scales, theme, things can get very, very complicated in there. And that's kind of where I kind of don't know all the things that you can do. I always end up looking up. There's just so many options for how you can make plots look. We'll show some of those. So the scales and theme, this is kind of the window dressing, right? This is, you're dressing the plot up, you're trying to make it look fancy, trying to make it look nice. That's where these two aspects come in. But the data, aesthetics, genomes, we have to have that. In every single plot, we have to have those three. Then facets, very, very useful. Okay, facets are very, very useful. And then we kind of get to the window dressing, the scales and the themes. So as I usually do, I'm going to try to stress the things that are required. Okay, so I'll try to tell you, all right, these are things that these are very important. And then when we get to the things that are more window dressing, I'll try to let you know that as well. Like, okay, this is something that's nice, but it's not exactly required on every plot that you have. Any questions? And this is how, so this is an example of what ggplot looks like. So you start with this ggplot, you tell it the data. A lot of times in this first part, you'll give it the aesthetics also, and then use the plus command. And then you say, okay, what type of geometric object do I want? What type of scales? Plus, what type of scales that I want? Plus, what type of facets? Plus, what kind of theme? So we're kind of adding things on. So it's a little bit like that piping, but instead of having that piping command, we just use the plus instead. So the statistical use of plots is to explore your data. There's something called exploratory data analysis. And this is really the first thing that I do when I have a data set and I have a question. I do exploratory data analysis. There's two sides of that. One, what is the variation within each variable? So there I'm talking about one variable, and I just want to know, what does that variable look like? That's the first stuff we're going to go over. So just single variable plots. The second one, what is the covariation between two variables? So there I have two variables and I'm interested in how they relate to one another. So there we're talking more about scatter plots. There can be a third variable here. There can be a second variable here. So what's the variation within one variable, but maybe I'm splitting up by another variable, for example, male and female. But really, those are kind of the main questions. The types of variables that we'll look at. So if I have one continuous variable, talking about a histogram, a density plot, or a box plot. If I have one categorical variable, bar chart. If I have one continuous and one categorical, and again, I can do a box plot by that variable, something we'll see. Two continuous plots, then we have a scatter plot, smooth line plot, so on and so forth. Okay, so going to use our Framingham data set. So let's all go over to RStudio and scroll down to this this second block here, the second block of text. And we're just going to hit that green arrow to get everything read in here. Okay, is that good with everybody? Okay. It didn't work, tell me, please. Okay. All right, so we got our data in there. We're going to use our Framingham data, and we've changed some of these variables to factors. Male, education, current smoker. That's going to help us a lot. So the first one, visualizations we're going to talk about are going to be histograms. And this is the plot I use the most. Always when I have a variable, particularly an outcome variable that I'm interested in, this is the first plot I will look at. If it's a continuous variable, is a histogram. Okay, we're all familiar with histograms, right? So let's look at the syntax here for this plot. Some of this is required. Some of this is more window dressing. So what's required here is this top part that I'm highlighting. So what I have, I always start with ggplot, and I tell it the data that I'm using. So ggplot Framingham. All right, so I kind of have that first box checked. Next thing is the aesthetics. I need to tell it what X variable I'm interested in here. Here I'm interested in systolic blood pressure. So I say X equals SYSBP, telling it. Plus histogram. And then really I could just end it there, just open and close. So let's go over to the, let's go over to here. I'm going to take just this first part. I'm going to copy it up here, and I'm going to remove this color and fill part, because even that's getting to sort of some window dressing. So this is all that is required, this code right here, to create a histogram. Just this right here. And this is what we're going to get out of that. So this shows us very valuable information about the distribution of systolic blood pressure. We can see where most of the values are. We can see that it's something called right skewed. Okay, it's definitely skewed to the right, slanting down here. And this, we don't see any bars down here, but it does tell us that there is some values out here at 300 towards the end there. It wouldn't show us, it wouldn't go all the way to 300 if there weren't any data at that point. But it tells us a little bit about the range of it too. The fill in the color arguments, again, this is just kind of a little bit of window dressing. I'm going to copy and paste this into the console, so it'll show me it right there. So the nice thing about having the fill in the color is I can see these individual bins a little better. It doesn't just look like one mass. So I can see what those where those bins are happening. And then the last thing that's added to the plot, it's just using some different labels. So here, the Y label is count. This is just changing it to count with a capital C. They're basically the same thing. On the x-axis, you can see by default, it shows the variable name, SYSBP. And in the plot over here, I'm changing that X label to systolic blood pressure, parentheses, MMHG. Okay, so just like a little nicer plot. And then adding an overall title, distribution of systolic blood pressure. This is all window dressing. If I'm just interested in the distribution, I don't need to do all this stuff right here. Okay, it's not required to look at the distribution, but if I'm showing this plot to somebody, that's when I might be interested in having all these aspects to it, all these kind of window dressing parts. The colors are, of course, things that I can change. There are many colors. And just Google search ggplot2 colors. And we'll get this document with all these colors that are available. And these here are only the named colors. So if I wanted to change the colors here, let's say deep pink and yeah, it's trying. So when I just hit enter, it's trying to show me the plot down here, which is not what I want to do. So I'm going to copy this and manually paste it in the console, so it'll show me over here in terms of this. So there's a bunch of named colors you can use. There's also something, if you've ever heard of hex colors. So these are usually done by the pound sign followed by a bunch of numbers. And these are two colors that I looked up this morning. F5842. I had to write these down. Of course, I forgot to copy and paste it again. And we have very nice colors here. Okay. That's the next colors. Yeah, I looked them up. These are the hex symbols for the official New York Knicks colors. Yeah.
Oh man.
Yeah, it's not orange and blue is not right. Orange and blue doesn't look quite right if you check it out. These are the official. So this next plot is the same thing. What do we notice? Anything you notice differently from this plot right here versus the top one?
Thickness of line.
Yeah, the thickness of the lines, and that is controlled by an argument called bin width. Okay, so here the bin width is 5. The initial plot, the bin width is about 7 or so. So the initial plot has a little wider bin width. We could go smaller here, bin width of 2. So why would we want to mess with the bin width? So here, I'm just going to plot in this bin width of 2 here. If I use bin width of 1, you'll see it'll get even smaller. So this one right here, clearly we've gone too far. the bin width here is too small. We've kind of lost the shape of the data. We're seeing all this just random variation that is going on here. It's harder to see the shape of the histogram in that one. Even the bin width equals 2, like for example, it shows a spike here and then it goes down. Does it really go down? Is systolic blood pressure at this value really lower? Probably not. It's just random variation. If we go back to this is the bin width equal, this is the default. This one's about 7. But we can go too far on this side. So let's say I bring it up to 20, then I've kind of lost the distribution there too. So bin width is something we don't want it too big, we don't want it too small. We kind of want a nice bin width to show us what the distribution looks like. And I like more detail. So I don't mind this plot. I would like the 5 one, the one with a bin width of 5. I like that better than the default one. I usually like a little more detail in there when I do a bin width. But anyways, this is something we're just looking at this. We want to know, hey, around where's the center? It's going to give us the range too. What's the distribution of it? Is it symmetric or is it right skewed? It gives us a lot of information. We can also see outliers here. So for example, if we saw a systolic blood pressure of 20, like if the range went all the way down to 20, oh man, we got an issue there. Okay, right away we know, hey, let's look at that data point. Let's look at that observation. Something went wrong there. Because systolic blood pressure at 20, I don't think he can be alive, right? No, I don't think so. Yeah. The next one, these are called density plots. So density plots are similar to histograms, but they're smoothed. Okay, instead of showing bins, this is going to show lines that are sort of a smooth approximation of those bins. Let's go down to the density plots here. And again, this has been fancied up a good bit. First off, I did the fill by male. I could remove that. And if I do this one, then we just get one value here. We don't get it separately for males and females. I'll show you another option here. I could say color equals male. Copy this, paste it over. So this looks similar to the plot that we have here, but instead of the figures being filled with the color with sex, it's just the outside. It's just the outside that has the color to it. So color, you refer to the outside. Fill is what's going to this is going to give us the inside part of it. And then of course we add the labels, make it look a little nicer. Instead of doing systolic blood pressure or SYSBP, we put systolic blood pressure. We have a title on there, and we fill it out. The alpha command is one we're going to use a good bit. Mostly alpha is a measure of how much you can see through the geometric object that you're putting on here. So alpha equals 1 means you can't see through what you're putting on the figure. Here we have alpha equals 0.4. That allows us to see through what we have on the figure. This one down here, notice I have alpha equals 1, and we can't see through the male is covering up the female density right here, and we can't see that the female density has this. So this plot is not very useful because it really doesn't show us the distribution for both males and females. It really just shows us for males. So adding the alpha equals 0.4, making it a little see-through there, and we can see the difference between those two. Staying on single variables, let's say we have a categorical variable. The simple way to look at this is through a bar chart. So again, we start the same way we did before. Genoplot, Framingham, AES, X equals education. Here, I'm just telling, I'm using genome bar. Okay, bar is going to create a bar chart. Again, I'm filling it with color, and then I'm adding labels. I'm using some theme stuff here. So this adds some bells and whistles to it. But again, the part that is necessary to do a bar chart is just going to be, the fill is not going to be necessary. Everything from that point is just adding window dressing. So we could just do it like that. Now, one thing that I don't like about this plot is that it has the NAs in there. Okay. Sometimes you could want the NAs in your bar chart, but sometimes you only want to show values where we know what the actual category is. So what we might want to do is, I'm going to I'll add all the window dressing to this plot down here. So you can just copy this text and paste it below. What we might want to do is get rid of those that don't have any education values. We're going to go to Dippler and our Dippler, using our Dippler vocabulary and our piping. How do we get rid of some values in the data set? What is the command that we use? NA.rm equals false. That's a very good answer. Okay, so we're doing a mean, and there's some NAs in there. We say NARM equals false, and that will only calculate the mean on observed values. Okay, so there may be an option in ggplot to do it that way, like an NARM equals false type of things, but I'm not aware of one. So I was thinking more when we don't want the whole data set, but we want a partial version of the data set. What is a way that we can do that?
Is it group by?
So group by is not what I was looking for.
Select.
What's that?
Select.
Select is what we use when we want to choose variables. Here we want to choose observations. So if I wanted to only choose a few variables, yes, I would use select. We're dancing around it. It's right there.
Is it filter by?
Yeah, filter, right. We can just use filter here, and we can use the is.na. There's two ways I can do this. There's always two ways to do everything, of course. I can put this right here. So Framingham, put the piping, filter, not equal to, remember that's the exclamation point, is.na of education. So this right here, this changes the data set that ggplot2 is getting. Now it's not getting the whole data set. It's only getting those that have a non-NA education value. So I can copy this and paste it over, and then we have a figure that's that has those going from it. And we could expand on here. We could mutate all within this one particular line if we wanted to. The other way we can do this, so ggplot2 can also use the piping option. It also has some ability to this will also work here. So here, what I'm saying, all right, let's start with Framingham. Then let's filter it by this. It doesn't have an NA for education. Then it's going to take that data set and it's going to give it to ggplot2, and ggplot2 is going to use it. So we can have a mutate up there. We could have a summarize up there. There's a lot of things that we could have before we give the data to ggplot. So it's similar to that'll give us the same thing. So either one of these ways could work, or you could just create a new data set too. So I could take this, I could create a new data set, Framingham EDU, just to note that it has the education value, and then I can use that Framingham EDU in here, and this will work the same way. So as always, there's a lot of different ways to do things. Find the one that works the best for you. People code differently. Honestly, I'm kind of an old school R person. I would probably use the last way. That's just kind of how I work. I would make a new data set and then feed it into there. So let's say I wanted to plot proportions rather than counts. Here I'm going to use something very similar. I'm going to start with Framingham, and then I'm going to get the count of how many, what do we have for each, how many do we have of each group? So count education, that tells us how many of each group are in the data set, similar to the table command. Then I'm going to mutate. I'm going to create a percent variable, which is just the this as a percentage. Then I'm going to feed that into ggplot. The x variable is going to be education. The y variable is going to be that percent. And then I'm going to add this genome col, which is going to create the columns that I want, and that gives me that column plot. Now, if I wanted to remove education, those that have NA for education, I would do that at the top. So I would start with Framingham, take those out that have an NA for education, then I would count. Okay, I don't want to count and then take those away for those with NAs. I would filter first, then count percentage, and everything else would be the same. And we'll get the nice looking plot here. So this plot has a lot of bells and whistles to it. It has the X label, the Y label, the title, and you see it has this theme part here, and it has this argument axis.text.x. So here we're manipulating some things about the x-axis text. So we have some high school diploma, some college degree. And what I'm doing, I'm setting angle equals 20, which makes these tilt like you see them right here. And H adjust equals 1 makes them start at the tick mark. Notice the difference between that and the default plot where it does not have any tilt to it, and it starts, the middle of it is at the tick mark. So a lot of options like this. And again, I don't have any of these things memorized. Whenever I want that, when I want, hey, I kind of like the x-axis to to tilt, which sometimes you need because sometimes they're very long, they'll kind of overlap one another, so you need to tilt them. I always have to look it up. I have to say, all right, what is that command? And then I have to look it up. Yeah. But it's something that you can do. Good question? Okay, just try. See. We'll see if there's a little exercise we can do, but we can go forward. Okay. So the next one here, this is when we have one continuous variable, one categorical variable. Okay, what can we do in that situation? This first one that we have is systolic blood pressure by sex. And for the syntax here, so telling it the data is Framingham, of course. I'm saying the x variable is male. So that's going to, on the x-axis, it's going to show the different sex values. The y variable is going to be systolic blood pressure. And then I'm using genome box plot here. So that tells it, all right, put box plots in each of these. And then we have the labels on top of that. What does a box plot show? The bottom line is the first quartile. The middle line is the median. The top line is the third quartile. There are definitions for how far out these whiskers go. And then the dots are sort of the very large values. So you can actually see all the values that are around there. The next one, this is a similar type of plot. Here we're just doing it by education. That one's a little complicated. I want to show you this one. So this is a violin plot. We're actually showing a violin plot and a box plot here. You can see that there's both of them. Has the box plot in the middle. The violin plot is what's on the outside. So the violin plot is very similar to these densities we looked at earlier. So it's a smooth version of the histogram, but it's just tilted on its side, and they have, and it's like a mirror image. So here, this is the density of systolic blood pressure for females. Again, mirror image. This is the density of the systolic blood pressure for males. So it gives us an interesting look at the difference between these two. Notice from this one, the outliers are much more apparent than in the density plots we looked at above. We can see that the outliers in the female group are much more spread out than the outliers in the male group. And we also have the box plots in there. Okay, so let's go down to the code for that, like violin plots. So just so you can do it, copy that code, paste it in there. Should give you something like this. Okay, so now I would like you, just as a quick exercise, copy that code, paste it down. To change this so that the X value is education and the Y value is cholesterol. So you may have to look, what are the variable names there? Remember, they got to be spelled right. And if you do that and that goes well, repeat it where you remove all those that have an NA for education. So just a quick exercise to get the wheels turning here and give you a little practice.
You said cholesterol?
Education and cholesterol.
Yeah. DOT, CHOM, with the C capital. Yes, something. Yeah, that's it. I think it was something. That, but we got the bird on it. David, you want? Yes, you don't need to put the data because you're good. Yes.
Okay. If you didn't get it, it's okay. Check your data set. So you can see here, I've started by with Framingham, filtering it, not equal to is.na for education, and then I'm sending it to ggplot. Now, when I do that, I don't have to tell ggplot what the data is. So I shouldn't put Framingham right in here because I'm giving ggplot the data through the piping. So I want to get rid of that data because the piping is going to give it the data. Then our X is going to be education. Our Y is going to be total cholesterol, which is TOTCH. There we go. Copy this. And then we get that. We get some warning messages. 49 rows containing non-finite values outside of the range. So that just means that we have some NAs for total cholesterol, and it gives us a warning message that it removes those NAs. If you ever, I really recommend playing around with these. If you ever have if you wonder what any of these commands are, for example, here we said genome box plot, we gave it a width of 0.1. Well, why did we do that? Well, let's make the width something completely different, width equal to 2, and see how it looks different. Boom. Okay, well, yeah, so then now all our box plots are wide and they're actually in the wrong location. So, okay, that's why we had that. The outlier size. We started with an outlier size of 0.8. What does that mean? Well, let's make it equal to 5. And then boom. Oh, okay. So that's the size of the points for these outliers. That's what that controls. So if you're ever interested in what one command means, this is what I do. I just will change the command to something totally different, see how it looks. You're not going to break the plot, right? You can always go back to what you had. And that'll give you some information. Yeah. Any questions about that?
When I copy the code from source to the console, I got a lot of plus symbols on the.
So you need a little debugging help?
Oh, I just copy the code from the R to the lower console. There's more like a left side, a lot of like a plus symbols. I don't know what happened. Why is that?
Gotcha. Let's I'll try to help you with debugging that.
Later is fine. Later, yeah.
We got a break in about 5 minutes, so we can that, and you can share your screen, and
Right.
I can try to help you see what's going on there.
Okay.
Yeah, I mean, but basically, um, if you're getting some error messages or this doesn't look right, check your data set. Maybe the Framingham isn't quite what it's supposed to be. So if we just do str of Framingham, we can look at that. Okay, are there a bunch of NAs in there? Then okay, something went wrong with the data set, and I need to go back and load it back in. If so one thing with this, if I use my normal run, on here, like this, notice it doesn't show me anything. There's nothing down here, and there's nothing up here. And even if I click this, it's not going to show me the plot. That is something to do with the particular version of RStudio. I think that's a setting. I don't recall what setting it is at the moment. So if that's something that's happening to you, that's why I'm physically copying the code and pasting it in here. Then what I have is going to show up in this plots window. If you run it from over here, it's supposed to come out down here. So you should see a plot down here. I'm not getting that for, I think, some setting that I have in RStudio. That's why I'm copying it over here so we can see it in the plots window. So if that's happening to you, it's happening to me as well. Nothing to worry about. Okay, I'm gonna skip over those. Okay, so all of that above, that is really looking at one variable, maybe one variable, one continuous variable by a categorical variable, but really all we're doing is looking at one variable. Where this starts to get a little different is when we have two continuous variables, like in this situation right here. So here we have age and systolic blood pressure, and we're looking at the relationship between these two. I want to know what is the relationship between age and systolic blood pressure. So the first thing I can do is I can look at a scatter plot of the data, really nothing else on it. So what do? ggplot, tell it Framingham, the data, the aesthetics, the X variable is age, the Y variable is systolic blood pressure, and then genome point. Now here I'm adding this alpha term. Alpha term is not required. Again, the alpha term is making these points a little more see-through, which is a good thing to do when you have a lot of points. When you have a lot of points and you just plot it, it'll just look like a big block of data. Okay, so using the alpha equals 0.3 makes things a little more visible. You can kind of see the data a little better. If you don't have a lot of data, you don't have to use that. And then of course the labels, all that is sort of window dressing again. But let's look at this plot for some different AES values. There's some different alphas, excuse me. So here's the plot with alpha equals 0.3. If I use the default, which is 1, you can see just the plots. It's just black. You can't see through the points or anything. So what's the difference? Well, let's take a look at age equals 50 here. Okay, so if I scroll, if I look up and down, age equals 50, I can see that most of the data points are there's a group right here, and there's a group right here. I can see that when alpha is equal to 0.3, so I can see some of the details. Okay, I can see that there's a little more data here, there's a little more data here. If I use the alpha equals 0.1, I can't really tell that as well. Okay, it just kind of looks like a big blob of data. That's what the alpha can do for you. So why are scatter plots so important? We can see the distribution of these variables. We can see outliers again, but we can see them in a different way. So let's take this point right here. Okay, this point right here. This point right here, its systolic blood pressure is high. Okay, it's a high systolic blood pressure, but it's not the highest. It's not the highest systolic blood pressure. So in terms of systolic blood pressure, it may not pop out as an outlier. The age, it's not an outlier for age, but the combination of the two is what makes it an outlier. So it allows us to see sort of weird data points instead of in one dimension, in 2 dimensions. Where's another one? This point right here, again, It's not a weird value of systolic blood pressure. Person's on the younger side. It's the combination of the two that makes this a strange point. So it allows us to see if we had a data point right here, for example, we'd be like, wow, that data point's weird. That data point wouldn't show up if we looked just at systolic blood pressure, wouldn't show up if we looked at just age. It's the combination of the two that makes that data point look strange. So we can see the overall pattern and we can see sort of these two-dimensional outliers. First thing we want to look at on a scatter plot. The next thing we want to look at is the trend between these two variables. Is it increasing? Is it decreasing? Is it a linear relationship? And for that, which we'll do after the break, we'll start to add some lines to this that will make the relationship between these two variables more apparent. Okay, so we'll come back at 11:15. This can head down to the third floor. Okay, all right, we are back, recording in progress. Let's go.
Yes, sir.
Okay, so we are talking about scatter plots, two continuous variables. First thing, we do it, we look at it, we can see where the data are, we can see each variable, we can see the combinations of the two, we can see overall trends and what's going on. But what I almost always want to do to a scatter plot is I want to add a line to it. I want to add a line that shows the general trend between these two variables. Now, what would you say here? As age increases, does systolic blood pressure seem to increase or decrease? It seems to increase. Yeah. Which is kind of gives us the general trend. Another thing I would note here as a statistician, I think the variability increases as age increases. It's not just that the overall trend is increasing. The data are getting more spread out as the person gets older. That can help us inform our statistical modeling. Here we are going to add a line to the plot we just did. Okay, we did that. So we're going to add a line to it. So again, we have this genome plot, GG plot. We have the genome points. What we're going to do here is we're going to add what's called a Loess line. Loess is a type of smoother. So the line that we can see here in red, this line can have some waves to it. It can go up, it can go down. It doesn't have to be a straight linear line. Okay, it doesn't have to be a line. It can be what's called nonlinear. Here, this looks remarkably linear. Okay, the line that we see here looks very straight. Okay, that's not always going to be the case, but the fact that that looks straight is very valuable to us as modelers. When we start to do regressions, when we're actually getting the relationship between these two variables, the fact that this is a straight line, super valuable to us, super valuable for us to know that. I'm going to go over here. Let's recreate this plot. We can copy the okay, and we can see the plot right here. I'm going to make a different plot down here. Instead of using systolic blood pressure, I'm going to use total cholesterol, like we did before. Of course, we got to change the labels here. Okay, I'm going to copy that one. See, we get a warning message again. Remove 50 rows, non-finite, missing value. Just means we have some missing values in the data set. Okay, so this is what the plot looks like. One thing, notice there's a zoom button right here. I can click this and I can make this plot show on the full screen. So we can look at this plot in all of its gory detail. And the reason why I wanted to show you this plot is because to demonstrate that the lowest line does not have to be linear. You know, the last one, it was just so linear. I wanted to show one where this one is certainly not as linear. There's an increasing trend between age and total cholesterol that seems to even out here at about 60 and then actually appears to go down a little bit. Just out of curiosity, do you think this actually goes down?
No.
No.
No. Why do you think it would show like look like it's going down on this plot?
The data number.
Oh, my bad.
No.
I was gonna say it's the way they collected the data, because it's the random variability with the people they asked.
Okay. So something about the sample.
Yeah.
Yeah, I think you're getting to that. Is that what you're gonna say?
I wanted to say the number of participants at a certain age is less than.
The number of participants is a very good point. And when we look at plots like this, when there's not a lot of data in one portion, this line can get kind of wild. And those are things that you want to kind of ignore. And when it's like, hey, there's not a lot of data there, let's not pay attention. So this is kind of that way. We don't have a lot of data down in this last portions. We see a little bit of decreasing. I do think it has to do with the sample. This is something we will call survivorship bias. People that have very high cholesterols are less likely to get to age 65 and 70. They're more likely to have coronary heart disease, heart attack before then. So the people are a little healthier at this. The people at this age up here had a little healthier lifestyle previously, or just didn't have bad cholesterol because of genetics. That's probably more of a survivorship bias, something with the sample. Yeah.
Another thing that I think it could be just because at that point you're on a constant stream of medications.
Yeah, medications. Yeah, that's a good point. Yeah, we're not looking at medications at all when we do this. Yeah, and that's actually we have blood pressure medication in this data set. I don't think we have anything with cholesterol, but let's go back to this one. So this one, yeah, this one just this is as linear as you will ever see a relationship between these two variables. You'll never see anything that is more linear than this right here. It's kind of astonishing. Maybe a little downward turn at the end, but very, very linear here for this one. So I am a big fan of the lowest line. So that genome smooth, where we say method equals lowest. Again, the color, that doesn't matter. That's just window dressing. SE equals true. That adds this shade that you can see right here. You can barely see it, but there's a little bit of shade. Shows some of the uncertainty in the estimate, which is a good thing to have on here. This is by far my favorite thing to do. Okay, we can add a third variable here. For example, let's look at the trend between age and systolic blood pressure for males versus females. We can do that by adding color equals male. The rest of the code here is the same as what we had up above, except for here, I have method equals LN versus method equals lowest. Let's run this one. Okay, so what's the difference here? method equals LM is only going to show linear trends. It's not going to show if it's nonlinear. So if I showed this with cholesterol, we would not see anything nonlinear when we looked at it. And we can even demonstrate that. Let's do this cholesterol one again. And I'm going to change it from lowest to LM. And again here. Okay, so then it shows linear. Okay, so method equals LM is only going to show linear. Lowest is going to show nonlinear trend. I don't like method equals LM, honestly. I've never used it, and I probably never would use it. I would only look at method equals lowest. So I'm going to change this from method equals LM to method equals lowest. Let's see how that looks. Still looks pretty linear for both of these variables. So what can we tell now? This is a very good comparison of the linear trend between age and systolic blood pressure for males versus females. Does it seem like there's a difference? Which one has a larger trend? Males or females? Females. Yeah, females appear to have a larger relationship between age and systolic blood pressure than the males do. The males start higher, but the age trend is more gradual than it is with females. So again, this tells us something that we will want to put into our statistical models. Hey, if we're looking at age and systolic blood pressure, we should take into account sex, but this also this points to an interaction between the effect of age and systolic blood pressure by sex. So this tells us, hey, if you run a model with this, I'm going to put an interaction term in there. That's going to be very useful. So looking at these figures is crucial, something we're going to do a lot when we start talking about linear regression. Okay. A lot of stuff on log transformations. I want to just go over this very briefly. Again, this is one of these things that is not quite as important. So this is adding a scales argument. This is looking at the diamond data set. What we're plotting here is the diamond price versus the carat size. And both of these variables, price and carat, are right skewed. Most of the values are down here, not getting as many values as we get as this increases. So what we can do is we can add this scale X to do on a log 10 scale, scale Y to do on a log 10 scale. Now notice the plot that results, the difference is not uniform. So we go from a price of 300 to a price of 1,000, $700 difference. We go from a price of 1,000 to a price of 3,000, $2,000 difference. 3,000 to 10,000, $7,000 difference. So that is a log scale. And on a log scale, this plot looks a lot nicer. Notice carat is also on a log scale. So sometimes that's you might want to employ that. I have in the past, but it's again another window dressing part. Here we're just talking about the alpha that we might be interested in. Okay, faceting. So faceting, this is kind of, I'd say, the fourth big thing to know. We set our data, we use the aesthetics, the X, the Y, we use genome to tell it what we're going to plot. The next thing is faceting. And here, this is what we use when we want to show, say, scatter plots separately by a categorical variable. So how we do that is first three lines are very similar to what we had before, just doing a scatter plot, smoothing here. This is using the LM smoother, so that's a linear. And then we say facet wrap tilde male. So that's going to plot one for males, one for females, side by side, one another. And you can see they have the same y-axis. That's always an important thing to note. Are they going to be the same y-axis or different y-axis? And we can see the linear trend in both of these. And this is something that I use very frequently. The next one here, same plot that we did above. What has been added is this scales equals free. So here, the y-axis scale is not shared between the two plots. The left scale, we got 100, 150, 200, 250, 300. The male scale, 80, 120, 160, 200, 240. Got to be very careful when you have different scales. Makes it harder to compare the two variables. The X scales on this are also not the same, but they're very, very similar. So it's hard to tell the difference there. You can see the 70 goes a little further for females versus males, but so scales equals free. That's going to free up the scales to be whatever they need to be. Sometimes you want to use that, but it's not always. Facet grid is something we want to use when we have two variables that we want to plot by. So here we are going to look at the trend between age and systolic blood pressure by sex and by smoker, non-smoker, current smoking status. So on the top we have females, we have males. Here we have non-smokers, we have smokers. Females, non-smokers, males, non-smokers, males, smokers, females, smokers. And we can see the trend of all those. So that's facet grid versus facet wrap. Okay, facet grid is going to create a grid of plots. Facet wrap is just going to show a bunch of different plots. We can do two variables on facet wraps as well. It just doesn't come out as this. Okay, a small little exercise for you. Two things that I'd like you to do. Let's take this. Let's take this first plot we did here. That's going to be this one. Okay, systolic blood pressure versus age by sex. I'd like you to do two things to change this plot. Let's, instead of making it systolic blood pressure and age by sex, make it systolic blood pressure and age by education. So let's change sex for education. Then, as I said, I don't like the method equals LN. Change it to method equals lowest. So change it to a lowest smoother versus the linear approach. So two changes to make there.
The copying that and basting there. There's a little filter thing again. Yeah. Yeah, no, those are the faster. Hello. The faster up is what, I don't know what. So it should say like faster around, you know, to put it like that. You had to drag this for a little bit. Just not it's a good thing, obviously. Yeah, that's all I have. It's from,
Yes. I downloaded it and replaced it, so now I got.
Yeah.
They got three new,
And it's like, for example, if you get any other things, it's something you close it, it doesn't close it all the way. You might get. It stays on, yeah. So this. But you know, like.
So we're still applying agents to start with. Okay.
So it doesn't damage the screen.
Go back, that's why it's.
Nice. Right here. What would you say?
No.
Yes, what was this to You should we do next week? Why not this week? Well, we got a hard work out. We gotta work. 10 to 1. What's wrong? Well, it's gonna be, because you know we got work, so like 6:30. That's what we're talking to, gotta be here. All 32. That's what I need. I just look at it all. Even
Okay. Yeah, capitals are good, yeah.
Actually, when they want to talk about comma, like it's.
Yeah, so here's my code for this, here's what the, plot looks like. And we can zoom in on this and, we can take a look at the values for, the trends for the different education levels. Now, I didn't change that. Oh, well. There we go. So see some nonlinear trends spark up here with those with a college degree and some college, particularly the college degree, there's something strange, but again, not much data right here, not much data on that side, so maybe we don't want to pay attention to those relationships, but still looks relatively linear for all of these, I think. One thing I don't love about this is that these plots are not all side by side. Makes them a little bit harder to compare to one another. If I wanted to make them all side by side, I would do that in the facet wrap function, and I would tell facet wrap n row equals 1. That tells facet wrap, all right, only use 1 row, don't use 2 rows. And when I add that to the plot, all these should occur side by side, making them possibly a little easier to compare to one another, since we have them all visually right there. Doesn't appear to be much difference, except for the last one looks a little funky, but that could be because there's not a huge sample size there. Great. All right, so the rest of the stuff that we are going to do is to just really add some bells and whistles to this plot. So the first one, you can see the labs command. We have title, then we have a subtitle. That's something that's going to be in have a smaller font right below the main title. Caption, okay, that's going to be in the bottom right hand corner. We've used X and Y. Fill sex, that's going to be this value right here. So instead of saying male, it's going to have sex for that. It starts to look a little bit fancier here. And what is this whole reorder command? Well, let's go over and let's take a look at this. Okay, first let's just plot it in, make sure we're starting with something that works. What the reorder command is going to do, it's going to change the order that the education level is going to occur on the x-axis. So here we have some college, then college degree, then high school diploma, and then some high school. So the reorder command tells ggplot, all right, my x variable is going to be education, but I want you to order it by the median systolic blood pressure. Order it by the median systolic blood pressure. So the on the left here, those have the smallest median systolic blood pressure, and that increases as we go to the right. So if we don't use the reorder command, if we just put education here, the only difference is going to be how the variables are going to appear on the x-axis. So now some high school is on the left, and high school diploma, some college degree, which is the natural ordering of the variable versus what we had above, which ordered by the median systolic blood pressure. So we could change that. We could order by the variance. So order by which the systolic blood pressure vary more in one group or another. So college degree has the smallest variance, then some college, then high school diploma, then some high school, which is actually the inverse of the natural order that we have. So it's just flipping that from one side to the other. Again, these are just bells and whistles, fun things that you can add to a plot. You can add labels to a plot using this genome label command. Again, not something I use a lot, but something you can use. There's a package here you can install which automatically changes where the labels pop out. So here, what this is doing is this is getting a data set best in class, which only contains cars. So it's a lot to explain here. I don't know if it's is it worth it there? Well, let's so let's So this MPG data set, I realize we hadn't talked about this one yet. This is a data set that has cars and some information about those cars. What year the car was, the manufacturer, the model, something about the engines, transmission, city miles per gallon, highway miles per gallon. What this command is doing right here, we're filtering it by class. And then what this command does right here, this gives us the rank of, change this a little bit, let's just, HWY rank. So I'm using row number, descending highway. This is going to give me what rank cars are in terms of their highway miles per gallon. And since I've grouped by class, it's going to be within each class. So this first car, this Audi A4, it has the 11th best highway miles per gallon, so on and so forth. And then I'm going to filter it to only keep those cars that have a rank of 1. So then I only have the cars that have the best, forgot to use my typing command. I only have the cars that have the best miles, highway miles per gallon. As we can see here. So then we are doing a regular plot. We're looking here at we're looking at miles per gallon by one of the engine factors, the displacement, and we're different colors for each class. And then what this label does, I'm saying I want you to label, use the model. The data is going to be this best in class. So that's only going to label those values, that only going to label those cars that are in the best in class data set. And when we do that, we can see 2 of these cars get pasted over one another. And that's where this second package comes in, where it'll actually move the labels around. Okay, now that I explained all that, really not important, nothing I've ever really used, but it's kind of a nice bell and whistle if you do want to point out some particular objects in your data set. Reference lines, these can be useful if you want to add a straight horizontal line or a straight vertical line to a particular plot. So here what we're doing, how you add the line, here we're using genome H line. So genome H line is going to add a horizontal line. Genome V line is going to add a vertical line. So I say genome H line, y-intercept equals 140. So it's going to have a line right at 140. Color equals blue. Line width equals 1. The type equals dashed. And that's going to create that blue line that you see on the plot. Then I add some text to that, which is actually very hard to see with this annotate command with various factors in it. Let's take a look at this. Again, this is not something I use all that often. Oh, here it's right here. Okay, so that's the line. And I think I lied to you. Yeah, genome belongs. Yeah. Sure. So this text that I'm annotating there, just telling you, okay, that's the hypertension threshold. Now it's way too big and it's right in the middle of the data, so it's very hard to see. So I'm going to change this. And first off, I'm going to make the size much smaller. I'm going to go from 7 to 1. Let's take a look at what that looks like first. Okay. Now it is very, very tiny. You can barely see on the left side. Okay. Went too far. Let's maybe try size equals 3. Okay, that's a pretty good size. But I don't like the location of this. I'd like to move this more over to the left. And I'm going to do that by changing this X value. X is where the text will be centered. Right now it's centered at 35. I'd like to move that over to a value of maybe, oh no, excuse me, that's where it starts. So I think I could maybe change it to 30. Let's try that. It's a lot of what you have to do with plots. I mean, it's never obvious of how to do things. Well, I'm back to size 1 again. I think we size 1. Still a little bit hard to see. I'm going to change this Y value to make that a little larger. So it increases. Okay, so now it's a little bit easier to see this label that we have on the plot. Another thing I could do, let's say I wanted to start a new line here. I can use \n to make it so that it'll say hypertension, new line, then it'll do threshold 140 milligrams. Boom. And then we have that. So that starts to look pretty nice, a lot more visible than what we had before. And this is, you can see why plots can take such a long time. It's a lot of like just trying, just trying things out. Does it work? Okay, no, let's change it up a little bit. Going back and forth, finding a place for this label here, for example, that works so that you can see it. Okay, so here you can tell ggplot the exact scales you want it to use. That's an example of that. Color scales are always fun. So you can make it so that the scheme of colors it's using is different. Let's take a look at this. I love looking at different color scales. So this one right here, this is the one. So you can see the colors here are kind of pastel colors. The default, just going to remove that color scale brewer. The default here looks relatively similar, but slightly different. Here's another one. Scale color Verdis C, option plasma. All right, you have some colors that look nice. And again, you can go wild in this. You can tell it the color scale gradient. You can say, all right, I want to start with fire brick here. I want to end with steel blue, and in the middle, I want white. That's going to start with red, fade to white, and then fade to this final steel blue color, and you can see what you get here. And I tell it the midpoint is equal to 0. All right, last thing is themes, and there's 2 important things to that I wanted to talk about with this themes part. The first part, notice that for this code, unlike the previous code, I'm saying base is equal to this ggplot command. We weren't doing that before. We were just running ggplot. Now I'm saying base is equal to ggplot. I want you to copy that, paste it over into your console, and hit enter. Nothing happens. Nothing happens when you do that. Nothing is supposed to happen. Okay, so all we've done, we've created a plot. This plot is called base, but we haven't looked at it yet. If we want to look at it now, I can just type base, enter. Okay, then now we can look at the plot. Okay, so why is this useful? So now I have this base plot, and there's different things I want to add to it using this theme command. First thing, I'm going to add theme_gray. this is the default theme in ggplot with that gray background and the white minor and major axes on there. Another one you can use is theme BW. This has a white background instead and gray major and minor axis lines to it. You can use theme minimal. This is actually the one I use most often. I like the white background better than the gray background, and I don't really like the bars around the plot. Theme minimal is a nice one. Or you can use theme classic, which takes out the grid and has sort of these classic XY axis lines. It's not a box all the way around. Yeah, and other things you can add to theme, any of the text, bless you, any of the text that is in the plot, you can change the font of it. You can make it bold or italicized, bigger, smaller. The legend position, previously that was on the right-hand side. We can change that to bottom with legend position equals bottom. So we can change that around. This is a very, very flexible framework. Saving plots. This is something I'd like you to run as well. So we can use GG save, which will write the most previous plot we created to your hard drive. You can do that as a PNG file, a JPEG file, a PDF file. So this is one right here. If we run this, this is going to write these files to a folder called figures. The figures folder we can see right here. And then boom, I have these two figures that as a PDF. Here's the one, here's the PNG file. PDFs work better for publications. PNGs work better for things like HTML and presentations. Okay, putting it all together, a publication ready figure. Wow, this is crazy. Okay, we're starting with Framingham. We're taking out all the education NAs. We're plotting age by systolic blood pressure. We're coloring it by education. We have a genome point, so we're going to see all the points here. We have a smoother. Here we're using a linear smoother. We're including a horizontal line at 140, which is where our hypertension threshold. We're changing the colors. We're changing the y-axis. We're using a facet wrap by mail. We're using a theme minimal. We're changing the legend position to bottom, and we have all kind of labels. And this is what it looks like in the end. So a publication ready plot, something that is very professional in appearance. You may think this is a crazy amount of code for one plot. So I added below here, this is actually my code that I use to create a plot. It goes in a proposal that I have. Just to show you that I use a similar amount of code here. I'm actually putting two plots together. The final figure is a PDF, which does not come out here very well. I think I can just open it up. Yeah. Everything about this plot I have thought about to the nth degree. I'll tell you that. The colors here, I have a particular color palette that I use where I think the colors are all easily differentiated from one another. This is a facet plot, but notice it doesn't just have, so this is the variable is the number, this is the number of variables. It doesn't just say the number, it says P equals. That's something that I have to change in the data set. Number of random effects, scaled root mean squared error, what method I'm using. the colors match here, which was kind of a challenging thing to do. So I have to make sure that this one particular method, it always has this sort of light blue color, which is my favorite color. So my method always gets that color, and making sure that that happens. There's different number of methods per plot. So just to say that, yeah, I take too much time on plots basically. But one of the benefits of R that I started with in the beginning, we were talking about Python versus R, is the quality of the figures you can make. And there's really, in terms of displaying data, there's almost nothing you can't. There's almost nothing that's impossible with ggplot. I mean, there's just so many. We've only scratched the surface here. There's so many options to it. Okay, we're at 12. We're at lunch. We'll come back at 1, and we'll start working on the lab. Okay, so for the lab today, I'm not going to do too much in the way of, I think pretty much know how this goes at this point. What the lab is going to have to do today is obviously with figures. There's going to be 3 questions you'll do. The first 2 will use the Framingham data. The last one is going to use the flights data set. On the lab here, it has just some quick things you could refer back to. Of course, refer back to the AM notes for more detailed examples, and you may need to do that. Also, at the bottom, section 4, remember this has a quick reference card with just some things that, so if you're unsure about something, this is a good place to check. So for the exercises, I'm going to ask you to complete exercise 1. This is going to be looking at single variables, not looking at covariation between variables, but just looking at single variables. Exercise 3, this is going to be looking at the covariation between variables. And then exercise 5 is going to be sort of the challenge problem here today. And if you want to do any of the others, certainly you can take a look at that. But the last one is going to use the flights data set. It's going to go back to yesterday's stuff where you're going to be joining some things before you create your plot. Okay, so that's all I have for today. You can get started.